All right, we're to section 3 of our unit 2 that covers limits, and we're going to try to find a better way to figure out what some of these limits are using our limit laws. There's going to be a lot of limit laws, just fair warning on this, but these are going to be them. So let's go ahead and set our standards here as to what we're going to be doing. We're going to be taking the limit as x approaches a of f of x and the limit as x approaches a of g of x. And we're going to assume that both of those exist. So if I'm taking the limit of two functions added together, that limit can go inside those brackets, and it turns out that I can take the limit of each individual function. So what my advanced calculus professor used to say is that the limit of the sums is the sum of the limits. So if you hear me say that, that just means that that limit can go inside. And in the same way, he would always say the limit of the difference is the difference of the limits. Because you got to remember that looks like a plus or minus up here. So we'll go back. It's not a plus or minus. There you go. Remember that these limits are just going to be numbers. They're going to be unique numbers that they are approaching. Okay? If I have the limit of a constant times a function, then this constant can come out here in front since it doesn't have anything to do with this x as it approaches a. So I could just do c times the limit as x approaches a of my function. We'll use that some today. There's definitely a shortcut around it that you'll probably pick up on. The limit of the products is going to be the product of the limits. So again, it distributes nicely into all of these, all right? Just the way that you hoped it would, the way it hopefully makes sense to you, it goes through. Okay? And finally, if I have the limit as x approaches a of a quotient, it does go to the top and the bottom. But of course, you got to be careful. You have to assume that g of x, excuse me, g of x is not your zero function. I might be coughing some today. I apologize for that. I'm just battling all sorts of allergy stuff. It is lawn mowing season in the thickest right now. Okay. So we're ready to evaluate some limits. So I got two functions up here. Looks like my f is going to be my pink function, and then my g is going to be my blue function. So first of all, we do the limit as x approaches 2 of this, of these functions. Okay. So that's going to be, if I work this out, the limit as x approaches -2 of f of x plus the limit as x approaches 2 of 5 times g of x. Remember what I said a while ago, if we have a constant there, we could actually pull that out in front of our limit. So it's going to be 5 times whatever the limit as x approaches. I forget a negative? No, if you want to. Of my g of x. Remember, when we do these limits, we talked about this in the last video. I'm not interested in what the value is at -2, just getting close to -2. So if I look at my f of x, as I get closer and closer to this -2 right here, I see my function value is getting closer and closer to 1. So it's just going to be 1 right there. And bring down the 5. Then the limit as x approaches -2 of g of x. So same spot right here. As you can see, I'm getting close to -1. So this problem is just asking 1 minus 5. So the limit of f of x plus 5 times g of x would be -4. Let's work b together. Don't have much room on here, so I'm just going to work b over here on the side. Again, the limit of the products is going to be the product of the limits. So I'm going to be able to split apart that f times g of x and take the limit of each individual one. And we're doing the limit as x approaches 1. Is that correct? So I can do the limit as x approaches 1 on my f of x function. See, I'm coming in good right there at the function value of 2. times limit as x approaches 1 of g of x. Well, it doesn't really tell me if it's a left-hand or right-hand limit, but remember, if the left hand and the right-hand limit don't meet up, the limit does not exist. So 2 times does not exist is still going to be does not exist. Okay, both of those limits will have to be defined in order to go forward on it. All right, you guys got C. All right, I want you to use your limit laws, find out what the limit of that quotient will be. So hit pause, and I'll work it out as well. Once again, you're going to get the limit to not exist. We got closer this time. It just turned out to be 0 on bottom. That's a no-go. Limit cannot exist if we got a 0 on bottom of a quotient. Got some more limit laws. Thought we were done with them. Ha, silly you. Okay, so limit law number 6 says that if I have the limit of a function raised to a power, this limit right here can just go inside. I can just take the limit, as x approaches a. Started my f a little too soon. It can go inside with the function. I can find out what the limit of that function is and then raise it to a power. Okay, so it doesn't matter what order you find that power in. You can take the whole function to that power, or you can just take the limit to that power, and it gives you the same thing. Limit as x approaches a constant, as x approaches a of a constant, is going to be the constant. This constant doesn't have anything to do with x. And so, of course, if I have a constant function, it is, let me just draw that out. If I have a constant function going across here, it doesn't matter what x is approaching. So suppose x is approaching that a right there. It's always going to be on this line right here at whatever that constant is. So in the same way, if I was to make it so that my function was this identity function, then the limit as x approaches a of that would just simply be equal to x. As x gets close to a, if I'm just having the x right there, it just goes straight in. Now if I have the limit as x approaches a of a power function, x to the n, then I am going to be able to do a to the n. More on that later as to why that works. The nth root of x, well, kind of the same idea. We didn't really put any parameters on here. N is supposed to be an integer. So suppose n's an integer here. It has to work the same. It would just be the nth root of a. So these are just ones that substitute right in. I get to put that a in right where the x was, as long as n is an integer. And the 11th one, suppose that I don't have a constant there, it's not an x, it's actually a function of x, then the limit can go inside if that's going to make life easier for you. So I can take the nth root of the limit as x approaches a of that function. And again, we're assuming n's an integer on that. It just makes life a little bit easier for us. So now that we have all these limit laws, we can work out a problem step by step into how to evaluate a limit without using a table this time. This will be nice. I'm not going to make my big f of x table and plug in values close to 5 to figure out what the function value is getting close to. I get to just plug it in right. I get to just use all my limit laws rather and figure out what it's getting close to. So first off, I'm taking the limit of a difference and the limit of the sum. So I'm just going to take the limit as x approaches 5 of each one of these terms. Notice my negative went out here. I could have done a positive here and then I left a negative on the 3, but that's just the way I did it. And the limit as x approaches 5 of 4. Now I got some constants in front. Okay, so I'm gonna pull this 2 out in front. So I just have my x squared. That's gonna make it so it follows the limit law. I got this 3 right here. So that way I just have an x back there. I had a limit law that looked exactly like this a while ago. And then if you pull the 4 out, you really don't have anything left back here. I want to have something left back there. if you feel the need to pull that 4 out, you're going to have to leave a 1 back there. I might as well just leave the 4 back there, okay? And that's going to work. Now, according to my limit laws, I can go back and give you numbers if I need to, but let me try to do that. So limit law, let's see, well, which one was that? Number 9 said that if I have x raised to a power, I can just plug that 5 in right there. Okay, limit law number 8 said that if I have just x, I still have x raised to a power, so it's kind of like 9 still. Again, I can just plug in that 5 right there. And finally, limit law number 7 said if I'm taking the limit of a constant, the answer is just going to be that constant every time. Please remember that. That idea is not going to go away anytime soon. So this gives me 2 times 25 minus 15 plus 4. That's 75 minus 15 plus 4. What happened? You guys just wanted me to redo the whole video. 50 minus 15 plus 4. And so I get a 39 right there. Some of you are seeing a shortcut on this. Why didn't I just take 5 and plug it in for all these? X is right here, because that's all this line right here was. That's true. And that is one way we're going to talk about calculating a limit, all right? But if I want you to calculate it using limit laws, I want to make sure you know these limit laws, because we're going to need to know all of these limit laws in full detail coming up later, all right? So it's a good way to check yourself, though. And it gets into the idea of what the next video is on. So we do use this idea. It's really cool what we use it for, but there is a lot of room to make sure that we know how to do these limit laws as well, okay? Tell you what, I think that you guys could try this one, okay? So go ahead and hit pause. I'll work it, you work it, and then we'll come back. Negative 1/11 on that. So the idea that on this last one, I could have plugged in -2 back in the beginning and got negative 1/11 and a lot less steps. It brings in the idea, oh, look what you've done. Oh my goodness. Oh, this isn't good. Where were we? We're here? All right. It brings in this idea, sorry about that, wrong button. It brings in the idea that we can do a direct substitution property. It says that if we have a polynomial, which we did 2 examples ago, or if we have a rational function, which you just had on the last example that you worked, and A is in the domain, that's the kicker right there, A is in the domain of F, then yes, you are correct. We can, in order just to take the limit as x approaches A of a function, we can just plug in the A into the function. I call these a well-behaved function, all right? They don't go off and do crazy stuff. There's not skips in them and jumps. There's no isotopes. I call it a well-behaved function just because it's a nice, smooth line that I can plug anything into, and I'm going to be able to find out what the limit is, okay? So with that being said, let's look at one that we cannot plug into, okay? We have a rational function here. So here's my rational function. Now, if I can plug in 1 into this and it's in the domain, I'm good. That's going to be my limit. It's going to equal my limit every time, I promise. But look at this domain right here. My x minus 1 cannot equal 0. X cannot equal 1. This is not in the domain of my problem. But lucky for you, we have some algebra techniques that are going to help us out. This first one's called the dividing out technique. So if I look at my function here, we might have worked this one on the last one where we did a table, I'm not sure. But if I look at my function here, I see that I could do a little bit of algebra on it. I'm looking at it, I could write this as an equivalent statement by factoring my numerator. Well, look what that did. Whenever I factor the numerator, I now have a common factor in top and bottom. And so what this gives me now is a well-behaved function. Now 1 is in the domain of this problem. I can plug in that 1 into this, and I get 1 plus 1 is 2. Now, if this isn't going on in your head, it needs to. You're saying, Mr. Lovely, how in the world did you take, is the limit as x approaches 1 of this function the same as the limit as x approaches 1 of this other function? Well, I'm going to show you how. Even though you might not have asked that, I'm still going to show you how. Okay, so if I graph this x plus 1, it is just this nice line right here. And if I take the limit as x approaches 1, we said that that was going to land right here at 2. Now, if you don't believe me, you can type this in a graphing calculator. But if I was to graph this top function right here, I'm going to put it in red, it looks exactly like this function, except, see if you remember this from pre-cal, it has a hole in it right there. All right. So it wasn't defined at that hole. What I did whenever I divided out this x minus 1 was I kind of filled in the hole to make it so that we can plug it in. So I'm telling you that all the function values on this rational function is the same as all the function values on this linear function at every point except for 1. Well, that's good news. I don't really need it to be the same at 1. I just need it to be the same as x gets close to 1 right here. And that's what I did. And I saw that I see that the value is 2. So I cheated a little bit on there. It's really cool how that works. I don't know if you're going to get that idea across in the video or not, but there it is. You need to hit rewind, listen to all that again. I felt like I explained it pretty well. Maybe in class it'll go a little bit easier to follow. Oh, we got a piecewise function here. Got a piecewise function. I'm wanting to know the limit as x approaches 1 of g of x, where g of x is, that's a poorly written piecewise function. I guess my math type didn't like that one. Okay. So, again, I'm crossing my fingers. I'm hoping that direct substitution works. I'm hoping I can plug it in and get everything to work forward on it. So, if it's in the domain, I'm good. So, I'm wanting to take the limit as x approaches 1. So, the question is, if I'm taking the limit as x approaches 1, which piece do I use, the top or the bottom? Remember, if you're in algebra class, I'm interested in what it's doing at 1. I'm not interested in what it's doing at 1. I'm interested in what it's doing when it gets close to 1. Close to 1 is not going to equal 1. So if I'm taking the limit as x approaches 1 of this piecewise function, I want to use the piece that's not equal to 1. I should have done a limit in there. I'm going to go back and do it. So it's the limit as x approaches 1 of x plus 1. Great news. It's a polynomial. It's defined everywhere. All right? It's a linear function. It's defined everywhere. So again, this one is just asking 1 plus 1, and that equals 2. Just showing you graphically real quick. You do have the same graph as you did a while ago, except for this time on the piecewise function, it cut out a little hole right here at 1. And it moved that hole to be up here at pi, 3.14. But again, I'm just interested in what it's doing when it gets close to 1, not equal to 1. So this value right here at 2 is what I was looking for. All right, let's look at some more algebra tricks to help me get through the. I really think we worked this one on the last video. I've slept since then. I've graded a lot of homework since then. I've worked with a lot of numbers since then. I've dealt with a lot of students since then. So it's hard for me to remember. Hey, I'm getting old. I'm getting really old. I'm turning 40 next year. I'm still trying to deal with that. This little smarting thing's kind of in the way. Is it bothering you guys? I'm trying not to make it bother me. So I got a nice rational function here, but immediately I see if I plug in 0 right there, it's not gonna be good. I'm gonna get a domain error. Okay, so I'm gonna have to think of something else. Well, let's just get rid of everything on top. not get rid of it, but expand it out and hope some stuff gets rid of. So I'm going to use binomial expansion on this. Binomial expansion says square the first term, multiply the 3 and the h together and double it, and then square the last term. I still have a rational function. I still have a function that I cannot plug 0 into. But look, it's going to simplify a little bit. And now everything that's left on top has an h. We've seen this before. That h I can factor out. Now that I factored out that h, I can divide it out using my dividing out technique. And I'm just left with the limit as h approaches 0 of 6 plus h. Now, you probably won't see me write out all my limit laws unless it asks me to solve something using limit laws. I look at this and I'm looking at taking 6 plus h where h is getting really close to 0. Well, 6 plus something really close to 0 is really close to 6. And so my limit on this one would be 6. You think you can try one? I'll let you tinker around with this one a little bit, all right? I'm going to have to throw you a hint. I don't think you'd get the hint. My hint on this one is multiply by the conjugate. Okay, so try that. Try to play with the conjugate on that. You might hit play into the video, see what I did, and then try to work it out. But let's try that, and we'll meet back up. So go ahead and hit pause. That 1/6 answer looks familiar, so I'm thinking we worked it in the last video. Okay, so my conjugate, I'm just going to work through this step by step, kind of tell you what I did. The conjugate, remember, I'm changing this sign right here in the middle. And so the whole reason of doing that is make it so that the top cleans up real nice. I got rid of my square roots. And so whenever I FOIL this now, square root times square root just leaves me with t squared plus 9. And then whenever I FOIL it, my outside and inside cancel. I have plus 3 square roots and minus 3 square roots. Boom, they're gone. And I have negative 3 plus 3 at the back end of this, which is going to be negative 9. And whatever I do on top, I got to do on bottom. So I'm going to have to take t squared times this quantity. That made it so that my 9's cleaned up nicely on top right here. And here's my biggest thing I can tell you. When it comes to cleaning up the bottom of a limit in a rational function, the limit of a rational function, don't do it. Just say no. Even if all your friends are doing it, you don't need to do it. There's no reason to do it. Just say no. Here's why. Because whenever I do my next step right here, I'm going to have a t squared left on top, and this t squared that I did not distribute through, or I guess try to distribute through, it's going to be tough to distribute through, this did not go through right here. All right, it didn't go through, and it made it so that it canceled, leaving me with the 1 on top. I have something a lot easier to take the limit of, and I ended up with 1/6. All right, before we go on with this lesson, I wanted to kind of jog your memory a little bit as to what we said the definition of a limit was. Our simplified definition of it said the limit as x approaches a of f of x is equal to L. It's going to equal that unique number L if and only if the limit as x approaches a from the left is equal to L, and the limit as x approaches a from the right is equal to the same number L. The same number L all the way through. Okay? So, let's go back to our absolute value function. I'm wanting to find this limit as x approaches 0. So is this a well-behaved function? We didn't really have anything for the absolute value function. Well, this is actually a form of a proof. I didn't even see that it said show right here. I'm telling you that the answer is 0. Okay? I want to show that mathematically that the limit as x approaches 0 of this absolute value function is 0. And so the best way to do that is going to be doing it using left-hand and right-hand limits. Before we get going though, remember that what we said about the absolute value function of x. Remember, it's actually just a piecewise function where it equals x if x is positive, and we take the opposite of x if x is negative. So for instance, if I'm taking the absolute value of -7, I would get -7 in order for it to equal something positive that we've always known to be true. Okay, so first up, I'm going to use the top piece. I'm going to use the fact that the absolute value of x is equal to x for all x. I use greater than or equal to 0. You can use greater than 0. So if I'm going greater than 0 on this, greater than 0 is going to be the limit as x approaches 0 from the right. If I'm taking the limit as x approaches 0 from the right of the absolute value of x, then it's going to follow the top piece, the limit as x approaches 0 from the right of just x right here, the same x. Well, this is just a well-behaved function. I can just plug in 0 into this, and I get that to be 0. That's not enough, though. In order to show it in a proof, I need to show that the left-hand limit and the right-hand limit both equal 0. So let's switch gears here. I'm going to do the other side of it, that equal -x, whenever x was less than 0. So if x is less than 0, that means I'm approaching 0 from the left, which means that I'm using a -x this time. Again, I have a well-behaved function. If you want to pull this negative out in front using a limit law, you can, but I can just plug in 0 right here, and I get -0. Well, there is no -0. Negative 0, getting close to 0 on the left side, is still going to be a 0. The fact that I got both of these equal to 0, I'm able to state my conclusion. So I'm going to say, therefore. Those 3 dots mean therefore. The limit as x approaches 0 of the absolute value function has to equal 0. And since we're doing a proof, we either have to do one of two things. We either throw a little box at the end, and that shows that our proof is done, or we put the initials QED at the end. Now, QED is something Latin, but it stands for, the English version of it says that which was to be demonstrated, quo estratum demonstrata or something. I don't speak Latin very well, so I just say quite easily done, and that suffices for me. All right, let's do another proof. I want to show this proof, this limit does not exist. And yeah, I'm going to do it the same way. Okay, I'm going to set it up, and I'm going to let you finish it. So I still want to take the limit as x approaches 0 from the right of this function. Okay, and I'm going to use my piecewise function to simplify it. And then I'm going to come down here, and I'm going to do the limit as x approaches 0 from the left of this function and work it out. You're going to work it out too. Hit pause, and then we'll come back. Same idea as the last one as far as simplifying these absolute values, but as you can see, I got 1 on one side, -1 on the other. They're not coming in at the same spot. We'll show this on the graphing calculator in class if you're here. If not, pull up Desmos or something and type in this function and see what's happening at 0. You should see that we have 2 functions coming in from the left-hand and right-hand side at 2 different spots. This one just asks if this limit exists as x approaches 4. So I'm going to have to do the limit as x approaches 4 from the left. And going all Bearcat colors. Did patriotic a while ago. And I'm going to approach 4 from the right. So help me out here. I got limit as x approaches 4 from the left. Which piece should I use? from the left is going to be smaller than 4. All right, so I'm going to use this bottom piece down here. I have a well-behaved function right here. I have a polynomial. I got a linear function. So that just means that this 4 can slide in right here. I could definitely use my limit laws, but it didn't say to. So I end up with 8 minus 8. Well, that's 0. So the limit's going to exist if I get 0 on this other half right here. Okay, so I'm taking the limit as x approaches 4 from the right. I'm going to have to jump up to this top one because 4 from the right is where x is greater than 4. So I still have a well-behaved function. And so I am going to be able to plug in 4 in for this x. So I get the square root of 4 minus 4. And sure enough, that is equal to 0. So since the left-hand and right-hand limits are the same, determine if it exists, yes. And actually the limit as x approaches 4 of this function f of x would equal 0. All right, now we're coming up on one of my favorite functions. It's called the greatest integer function. It feels like a trumpet should play every time I say that. Greatest integer function. Dun, 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 dun. But it doesn't. I need to get a little soundboard in here, though, or something that will do that. All right. Let me see what my slides say real quick. Show that. Definitely not ready to show anything on greatest integer function. Show that. All right. So greatest integer function, the way that I write the greatest integer function is I put an x. You probably saw some last year in your pre-cal book, and I just graciously skipped over it because we had enough parent functions going. But I'm seeing it now in Algebra 2 books where they're introducing this greatest integer function along with the squaring function, the cubing function, the square root function, the cube root function, the absolute value function, all of those, and they just put this in there with it, okay? And so my definition of the greatest integer function, how I evaluate it, is it's going to be the largest integer that is less than or equal to x. Less than or equal to x. For example, if I have the greatest, I'm taking the greatest integer function of 4, the largest number, integer, whole numbers and their opposites, that is less than or equal to 4, well, it's easy, that'd be 4. Okay. What about if I do pi? It's making me hungry. Pi. So we know pi is 3.1415, whatever it is, repeating decimal on forever. And so if I'm doing pi on this, the largest number that is less than pi would be 3. And that would be the answer. And so it's not too hard to work, is it? Switch colors on this one. You think I can throw you off? Not by the color, but look at that negative sign. Ooh. What do you think on this one? Hope you didn't say -2. All right. Has to be smaller than the number. So, smaller than -2.8 is -3. That's the nicest number, whole number, or integer that's smaller than -2.8. All right. I think that's enough of that. So I think now we can show, let's pull this, oh, I erased it. I was going to pull it over. I'm wanting to show that, I guess I couldn't find this in my math type. The limit as x approaches 3 of the greatest integer function is not going to exist. Again, I'm showing I got a left-hand limit and a right-hand limit. Just get used to writing all of that out. Okay. So let's just do the right side first. The limit as x approaches 3 from the right side of the greatest integer function. So what I want you to imagine doing is plugging in something that is just a little bit bigger than 3 into x because I'm approaching 3 from the right side. So let's just take like 3.01. I don't know if we just did this on one of the examples I did or not, but 3.01, I guess it'd be like pi, 3.14, the largest integer that's smaller than something that's approaching 3 from the right side would have to be 3. If you didn't quite get that, we're going to do it again. We're going to go from the left side, though. Imagine, not to give it away or anything, imagine approaching 3 from the left side of the greatest integer function. Okay, approaching 3 from the left side, not at 3. Not at 3. This is not a well-behaved function. I don't know if we're going to be able to graph it in the graphing calculator or not, but this thing looks terrible in the graphing calculator. There is breaks everywhere. It's not a well-behaved function. So being able to just take that 3 and plug it in for x and write the answer cannot happen on the greatest integer function. And here's why. Because if I plug in something that is just a little bit smaller than 3 on this, a little bit smaller than 3 would be like 2.99999. Imagine the largest integer that is smaller than 2.99999. It's not 3. It's going to be 2 in that case. Okay? It's going to be 2. These are not equal right here. Not equal. So, therefore, the limit as x approaches 3 of the greatest integer function does not exist. Used a little box last time. I'll go with the quite easily done this time. We're getting so close to the end, I can smell it. All right? It's either that or the lunch that people left in my room today. I'm not sure. I can smell one of the two. Got a couple theorems here. We have one theorem that's going unnamed. We will name that in class. I have no way. I'm 3 weeks ahead on these videos. I have no way of knowing what you're going to name this video in, or what you're going to name the theorem in 3 weeks. So I'm just going to call it theorem 2 right here. It says f of x is less than g of x when x is near a, then the limits of f and g both exist as x approaches a, then the following is going to be true. So if you have f of x is smaller than g of x, you can take the limit as x approaches a, and it will always be smaller than the limit as x approaches a of your g of x. I was going to use this picture down here. I'll explain that more in class or on a Google Meet later, but what that does is it sets up our squeeze theorem. Our squeeze theorem, it's also called the sandwich theorem. I've just chosen to use squeeze because I think that your book does. The squeeze theorem says that pretty much if you have g of x that is sandwiched between f of x and h of x, when x is near a except possibly at a, then what happens is you can take the limit of your two outside functions. If we're calling it sandwich theorem, we could take the limit of the bread, and we could find that it's equal to L. If they're both equal to L, then the following has to be true. Then the limit as x approaches a of g of x is equal to L. Let's look at this two ways. Okay, I can look at this the first way, and just suppose that my g of x is the number of calories that I eat. Okay, and let's suppose that this f of x is the number of calories that a freshman eats on any given day. And so I always eat more than a freshman. Sometimes we're equal to, but I always have more calories in my day than the freshman. But there's a senior, he always has more calories than me. So what's going to happen is there's going to be this random day that this freshman and the senior are both going to eat the same number of calories. If that's the case, and I always eat at least as much as the freshman, but I always have less than or equal to the number of calories that the senior has, then I'm guaranteed that day that I'm going to eat the same number of calories as both the freshman and the senior. Okay, so they both eat the same number of calories, L, in a day. Therefore, the number of calories I eat in a day would also be L. If that didn't make sense, let's look at it graphically. All right. So we're getting close to A right here. And what happens is my h of x is always larger than my g of x when we're getting closer to A. And then my g of x is always larger than my f of x when I'm getting close to A. And so that means that my bottom guy down here, f of x, it's always the smallest. And so, as you can see, what happened right here is that my largest function, this green function right here, it started squeezing down towards my smallest function, my f of x, started squeezing up, and I'm left with this pink function right here in the middle. The number of calories I ate in a day has to stay squeezed or sandwiched between those two. And so, if I can calculate what the limit is of this green line right here, and I can calculate what the limit is as x approaches A of this blue line right here, I'm guaranteed that the limit is going to be if they're the same, the limit of this red line is going to have to take on that same value. Okay? I might have way over explained that, but let's see what it looks like in an example. This will be it. Thanks for bearing with me again. You guys are totally awesome troopers for doing this. Especially if we're having to be quarantined and you're watching this at home, or if you're having to be quarantined and watching this at home, or if you just get bored and watch this video at home. So, I've got this limit. I'm wanting to show that it's equal to 0. I won't get too far with my left hand and right hand limit on this. Okay, so I'm probably going to throw out a big hint like use the squeeze theorem to show that this is equal to 0. Or if you see a sine or cosine function, that's a pretty strong hint if you're needing to prove that a limit does not exist or does not, or if you're wanting to show that it equals 0, that's a pretty good hint that you should use the squeeze theorem as well. Okay. So unfortunately, I cannot just say that the limit. So some of you might be thinking, well, let's just take the limit of x squared. Let's just go back to the beginning of the video and take the limit of each individual one as x approaches 0. Does not work. All right, that wasn't one of my limit laws that I was able to plug that in right there. It's not in the domain, so that's not going to work, unfortunately. So what I'm going to do is I'm just going to break this down. And like I said earlier, I said always look to use this squeeze theorem when you're dealing with sine and cosine. And the reason is because I can take out this part right here where I'm taking sine of this angle, sine of 1 over x, and I know good and well that sine has to stay between -1 and +1. Think about the sine graph. It just oscillates -1, +1, -1, +1 as it goes down the graph. Okay. Now, my goal is to make this middle look like the top. And so, as you can see, all I need to do to make it look like the top is multiply everything by x squared. So if I multiply the -1 by x squared, I get -x squared. If I multiply this middle by x squared, I get x squared times sine of 1 over x. If I multiply the 1 by x squared, I get x squared. So here's where the squeeze comes in. I'm saying that this always has to be true because of the way that the sine function works. So now if I can take the limit as x approaches, what are we approaching, 0, of the bread out here, of my big function and my small function, that's a well-behaved function right there. 0 squared is 0. This is going to be 0. Then I can assume that this middle part coming down is going to equal 0. Now you can't just write that down and say that. You have to tell me what you used on this. So tell me that's true by the squeeze theorem. Okay? Because it looks like I just made all this up. But once you tell me, hey, that's by the squeeze theorem, I'm like, hey, that's what they did. They found the bottom, they found the top, so this middle had to have the same limit. Okay? Whew, that's all I got. And man, I like this stuff a lot better than some of our previous videos. So hope you enjoyed it. Work some problems, have some good questions ready for me, and I'll catch up with you guys next time.